Hello everyone. In this video lecture, we will be discussing in details about the Maxwell's equations. So, the first Maxwell's equation is the Gauss's law, which is given by divergence of the electric field is equals to rho by epsilon naught, where rho is the volume charge density. But all of you know about the Gauss's law in its integral form, which is E dot d of s is equals to q enclosed by epsilon naught, where q enclosed is the charge enclosed by the closed surface. Now we will prove that both the differential form as well as the integral form, they are equivalent. That is, we can get one from the other. Let's see how. Let's give an equation number, both of them. Now, before trying to see the equivalence, we'll have to know about the divergence theorem. What the divergence theorem says is that the divergence of any vector, we can consider a vector to be f. So, if we integrate the divergence of any vector over a volume V, then this is equals to integral of that vector dot d of s. So, we can replace the vector f here by the electric field E. So, in our case, the divergence of the electric field integrated over a volume V will be equals to integral E dot d of s. Let's give this equation number 3. Now, let's apply this divergence theorem to equation number 1. So, from equation number 1, we get divergence of the electric field is equals to rho by epsilon naught. Now, let's integrate both the left hand side and right hand side over a volume V. So now you can see that the left hand side from the divergence theorem can be written as E dot d of s. So you see, the left hand side of the equation 3 is del dot E integrated over a volume V is equals to E dot d of s. So instead of this left hand side, we can replace it with E dot d of s. So we will replace this with E dot d of s, rho by epsilon naught d of v. Within bracket, you can write from equation 3. So now the right hand side of this equation is rho integration of rho d of v. So now, as I have already discussed, rho is the volume charge density. So now If we integrate the volume charge density with the volume, we will get nothing but the charge enclosed. Epsilon naught is a constant. So we will get 1 by epsilon naught rho dV, integration rho dV will give us charge enclosed. So you see, we get back our integral form of the Gauss's law. The second Maxwell's equation can be written as divergence of magnetic field is equals to 0. Now the question arises, why is the divergence of magnetic field always equals to 0? In order to understand this, let us consider an arbitrary volume V and consider that magnetic lines of force are passing through this volume V. So now the divergence of magnetic field will give us the net magnetic lines of force that is passing out of the surface. So if there are no sources or sinks of magnetic field inside this volume, then the net amount of magnetic lines of force that have entered inside the volume will be the same as the net amount of magnetic field that is exiting the volume, right? Because no magnetic lines of force is being generated inside this volume, nor is it generated, nor is any magnetic lines of force being consumed within this volume. So what is going to happen is the number of magnetic lines of force that is entering the volume will be the same as the number of magnetic lines of force that is exiting the volume. So if this is the case, that the number of lines of force of magnetic field entering is equals to the number of lines of force exiting the volume, then we will write it as divergence of magnetic field is equals to 0, right? The case when the divergence of magnetic field is not equals to 0 can only be written if there is a source of magnetic lines of force inside this volume or a sink of magnetic lines of force within this volume. But the thing is, we cannot have any sources or sinks of magnetic lines of force. Like we can have for electric charges, positive charges, electric lines of force emit from a or come out of a positive charge and they terminate at a negative charge. But such things do not happen in case of magnetic lines of force. Suppose we have a bar magnet such as this, and we have a north pole and south pole here. Magnetic lines of force will come out like this, and magnetic lines of force will not terminate in the south pole here. What they will do is they will continue towards the north pole inside the magnet also. Okay, so the magnetic lines of force never terminate or never originate from a certain point. They are always continuous. So you cannot have a source or a sink of a magnetic lines of force. So if this is the case, then if we draw, let me draw a few more magnetic lines of force, something like this. So magnetic lines of force will be always continuous. Now if you draw an arbitrary volume here, what will happen is the number of lines of magnetic lines of force entering the volume will be the same as whatever is exiting the volume. Now, if we draw an arbitrary volume encompassing the south pole, even here also the same thing will happen. Whatever magnetic lines of force have entered the south pole, they have also exited the south pole here, right? So similarly, if we take a volume encompassing the north pole also, whatever magnetic lines of force have exited from the north pole will again enter the north pole inside the magnet. Okay, so magnetic lines of force are always continuous, and we do not have any sources or sinks of magnetic lines of force. So that is why we can always write divergence of magnetic field is equals to 0. The only case when divergence of magnetic field will not be equals to 0 if we can find something called as a magnetic monopole, where we can write something like north pole, magnetic lines of force coming out of a north pole, something like this, just in case, just like a positive charge, electric lines of force exiting a positive charge, or if we can find a south pole at which the magnetic lines of force terminate into a south pole. If we can find such magnetic monopoles, okay, only in that case can we have the divergence of magnetic field being not equals to 0. But we have not been still able to find any definitive proof of monopoles existing. So till the day we are able to discover any magnetic monopoles, the second law of or the second Maxwell's equation, where the divergence of magnetic field is equals to 0, will hold valid. Or we can also say that magnetic lines of force will always be continuous. In the next video lecture, we will discuss about the third Maxwell's equation, which is the Faraday's law. Thank you.